The objective of magnetic confinement fusion is simple. Pack as much fuel into the plasma as possible. Fuel density is the primary variable that determines the scale of the reactor's energy output. This is the thermonuclear power equation. Notice the variable n representing fuel density. Because the power output scales with the square of the density, doubling the fuel doesn't just double the power, it quadruples it. Achieving high density is difficult. Since 1988, reactor engineers have operated under a strict empirical ceiling known as the Greenwald limit, which caps the density of a plasma before magnetic containment fails. The Greenwald limit is calculated by dividing the plasma current by the area of the reactor's cross-section. This ties the maximum achievable density directly to the physical dimensions of the machine and the electrical current driving the plasma. This chart plots historical operational data from the K-star reactor. The solid diagonal line marks the 1.0 Greenwald limit. Almost all thousands of recorded plasma discharges, plotted here in red and blue, fall strictly underneath that line. To safely generate more power without crossing that threshold, engineers had to increase the physical volume of the reactors. The multi-billion-dollar scale of international projects like ITER and GEMO was a direct response to this mathematical constraint. For 30 years, physicists treated this empirical boundary as an absolute physical law, assuming massive machines were the only path to high-yield fusion. Recent experiments have proven that this assumption is no longer valid. The evidence comes from China's experimental advanced superconducting Tokamak, known as EAST. Working with international collaborators, EAST engineers stabilized a plasma at a density 65% beyond the Greenwald limit. This chart visualizes the shift. While historical data clusters safely below the threshold, the EAST experiment placed a stable data point 65% above the previous danger zone. Typically, pushing a plasma this far triggers a violent disruption, tearing the magnetic fields apart. But the EAST plasma held its shape in a high-performance state termed a density-free regime. The team achieved this by ignoring the limit itself and instead manipulating the specific conditions present the moment the reactor was turned on. The EAST data shows that the Greenwald limit is an avoidable engineering bottleneck, rooted in how the plasma interacts with the physical reactor hardware. High density alone does not cause plasma collapse. The collapse is driven by the reactor's walls. A Tokamak vacuum vessel is lined with heavy, heat-resistant tiles designed to withstand extreme thermal loads. These tiles are typically made of tungsten, a metal chosen for its exceptionally high melting point. As fuel density approaches the Greenwald limit, the outer edge of the plasma becomes agitated. Energetic particles at the boundary break containment and strike the surrounding tungsten tiles. This collision causes physical sputtering. The kinetic force of the plasma knocks individual tungsten atoms loose from the solid wall. These loose tungsten atoms migrate inward, crossing the magnetic boundary and entering the superheated core of the fusion reaction. Once inside, the heavy metal acts as a heat sink. The tungsten atoms absorb the plasma's thermal energy and radiate it away, cooling the surrounding fuel. Because the magnetic fields require extreme heat to maintain their structure, this rapid cooling degrades the plasma's confinement. As confinement degrades, more plasma strikes the wall, knocking more tungsten into the core and cooling the edge even faster, until the entire reaction collapses.
The Greenwald limit is the mathematical point where this runaway sputtering sequence begins. By stopping the sputtering, you effectively remove the density limit. To solve the sputtering problem, the EAST researchers applied plasma wall self-organization theory, or PWSO. PWSO theory argues that a plasma's ultimate density limit is determined by the specific boundary conditions established in the first few milliseconds of ignition. This timeline charts a typical plasma discharge. The focus here is strictly on the ohmic startup phase, the exact moment the machine powers on and the plasma is first formed. During a standard startup, engineers use intense electrical currents to heat the gas. This aggressive heating instantly triggers physical sputtering, flooding the chamber with tungsten before the plasma has even stabilized. Supplemental heating methods like neutral beam injection can make this worse. Data from the French Alternative Energies and Atomic Energy Commission shows that injecting high-energy neutral beams induces a rapid rotation in the plasma. The The resulting centrifugal forces actively drive heavy tungsten ions into the core. If the core is polluted during startup, the cooling loop is already primed. Increasing the density later in the pulse only forces the tungsten to radiate more energy, causing a disruption long before the reactor reaches peak performance. Surviving the high-density regime requires a startup phase that generates extreme heat without disturbing the tungsten walls. The East team achieved this by managing initial fuel gas pressure and introducing a different heating mechanism. They replaced the traditional startup sequence with Electron Cyclotron Resonance heating, or ECRH. This comparison shows the shift. Instead of brute force electrical current, ECRH uses highly focused microwave fiends, tuned to excite only the plasma's electrons. This raises the core temperature rapidly while keeping the outer boundary cool and tightly organized. Because the boundary remains calm, the plasma edge barely interacts with the tungsten tiles, nearly eliminating physical sputtering. By completing the startup phase with an unpolluted core, the reactor avoids the initial impurity accumulation that normally triggers a density limit. Without heavy metal acting as a heat sink, the radiative cooling loop never begins. The engineers can safely increase the fuel injection, pushing the plasma smoothly into the density-free regime. ECRH bypasses the conditions that make the Greenwald limit lethal, allowing the plasma to scale past the 1.0 threshold entirely. Optimizing the startup phase translates directly to the design of future commercial power plants. This methodology scales to next-generation projects like the European Demonstration Fusion Power Plant, DEMO, and the ITER experiment. Because fusion power scales with the square of density, operating a machine like DEMO at double its planned density generates 4 times the total energy output. For ITER, the engineering implications are equally practical. With the density restriction removed, physicists can hit their target output of 500 megawatts of fusion heat using lower electrical currents. Dropping the operational current below the projected 15 megaampere requirement reduces the thermal and mechanical stress on the reactor's cooling systems. Lower currents also provide better control over the magnetic fields, reducing the risk of disruptions damaging the vessel. The successful experiments at East prove the Greenwald limit is not absolute. By mastering the first milliseconds of ignition, researchers have provided a blueprint for stable, scalable, and commercially viable fusion power.